In chapter 7.5, we study systems of inequalities. Now, before we get into systems of inequalities, let's talk a little bit about inequalities in two variables. Now, back in chapter 2, we studied inequalities involving a single variable. The solution to an inequality of a single variable could be shown on a number line. For example, we had an inequality, a polynomial inequality, x squared minus 4 is greater than 0. You might recall to solve these polynomial inequalities, we decided we wanted to factor. Factoring would then allow us to determine our critical points. We would take those critical points, the critical points were the zeros, in this case, -2 and 2, plot them on a number line, and we would choose test points on either side of the critical points in between each critical point to plug into the original inequality. If we tested, say, for example, -3, if we plug that in, -3 squared would be 9 minus 4, which is greater than 0. That made our inequality statement true. We put a little check mark above that region. We tested a point between -2 and 2, say, for example, 0. If we plug in 0, we get 0 minus 4 is greater than 0. That is not a true statement, so we put a little X above that one, and we chose a test point to the right of 2, say, for example, 3. Plug it in, that gave us 9 minus 4, which is 5, which is greater than 0, a true statement. And then we shaded in the true statements and left the false statement blank. At the endpoints, we put a parentheses in this case because this was just greater than. If there were an equal to component, we would have used a bracket. Hopefully that's a little bit familiar. Here, we study inequalities in two variables. So one variable, we just had an x. Now we are going to have an x and a y. The solution to an inequality in two variables is a region of the graph. So this is going to be on a coordinate plane. The region of a graph that contains all points that make the inequality true. Shading is used to show the region. So here are our steps for sketching a graph of an inequality in two variables. So only two steps. Step number 1, replace the inequality sign with an equal sign and sketch the graph of the resulting equation. Use a dashed line when we're dealing with less than or greater than, and a solid line when we are dealing with less than or equal to or greater than or equal to. So if there's an equal to component, use a solid line. If there is no equal to component of it, just use a dashed line. Then choose a test point that is not on the curve to plug into the original inequality. If the point makes the inequality statement true, shade the region bounded by the curve that includes the test point. If the point makes the inequality statement false, shade the region bounded by the curve that does not include the test point. Let's look at a couple quick examples here. Sketch a graph of the inequality. 5x plus 3y is greater than -15. Notice this is an inequality in two variables, x and y. We want to begin by sketching the line 5x plus 3y equals -15. And yes, this is linear. Notice that the degree or power associated with x and y is both going to be 1. This is a line that's written in standard form, ax plus by equals c. If we're sketching a graph of a line, a lot of you like to rewrite the equation in slope-intercept form. That's perfectly acceptable. Personally, if I have a line that's written in standard form, I think it's easiest just to plot the intercepts. Notice, if I plug in 0 for x, that will give us the y-intercept. If I plug in 0 for x, I get out the y-intercept. Well, that makes this term equal 0. We have 3y is equal to -15, which means y is equal to -5. There is my y-intercept. And to find the x-intercept, all I have to do is plug in 0 for y. That gives me 5x is equal to -15, meaning that x is equal to -3. I can plot that point, and once I have 2 points, I can draw in my line. Now notice, I've used the dashed line here because there is no equal to component of this inequality. It's just greater than. After we draw our line, We choose a test point to plug into the original inequality. You can pick any point that is not on your line or on your curve. A lot of times, if possible, I strongly suggest picking the origin. Plugging in 0 for x and 0 for y is generally fairly easy to do. If we plug in 0 for x and 0 for y in the original inequality, we get 5 times 0 plus 3 times 0 is greater than negative 15. 0 is greater than negative 15. And this is a true statement. Because plugging in this test point resulted in a true statement, I want to shade the region that includes that test point. That means we're going to shade everything up and to the right of our line. And there is our solution set. Any point that is in this shaded region will be a solution to the original inequality. Notice we use a dotted line because the points that are on the line are actually not solutions. Okay? Any point in the shaded region will satisfy the inequality. Let's look at another one here. Sketch the graph of the inequality. We have x minus 1 squared plus y minus 4 squared is greater than or equal to 9. We begin by sketching the curve x minus 1 squared plus y minus 4 squared is equal to 9. Now this looks a little bit funky. I've got an x squared term and a y squared term. You might remember this is actually the standard form for the equation of a circle, right? X minus h squared plus y minus k squared is equal to r squared. In this format, h and k, that's the center of the circle. Whoa, h and k is the center of the circle. Sorry about that. Let's erase that there. H, the center of the circle, and r is the radius of the circle. Well, in this particular case, h is going to be 1, right? X minus h. K is going to be 4, y minus 4. And r is going to be equal to 3, right? 3 is the square root of 9. And so this means we have a circle with a center located at 1, 4 that has a radius of 3. So to draw our circle, the easiest way is to start with the center of the circle. And because we have a radius of 3, we know that we have to go 3 units up, 3 units to the right, 3 units to the left, down, 3 units to the left. All right, 3 units all the way around that center point. And that gives us our circle. Now, after we draw our line, or our curve, in this case, and notice I used a solid line as opposed to a dotted or dashed line because this has the equal to part associated with it. Next, we choose a test point to plug into the original equation. Now, the origin is always an easy test point to choose. However, if you're working with circles, there is one other point that is even easier than plugging in the origin, and that point is actually the center of the circle. All right, if we plug in 1 for x and 4 for y into our original inequality, we get 1 minus 1 squared plus 4 minus 4 squared is greater than or equal to 9. And, well, by plugging in the center, actually each of these goes to 0. We get 0 is greater than or equal to 9, which is not a true statement. So because this point right here gives us a false statement, we want to shade the region that does not include our test point. That means we want to shade outside of our circle. And any point in the shaded region or along the curve, in this case, will satisfy the inequality. All right, points that are on the circle will satisfy the inequality because we have this equal to component of the inequality. All right, so that is solving inequalities in two variables. Coming up next, we're going to talk about solving systems of inequalities.